All right. Hello. Yeah, so we just had an email. That they're lifting some of the COVID restrictions, which is exciting. Classes, though, we still have to wear masks. But then offices, that seem to be up to discretion. Like if you're in my office, if I do tend to have often 4 or 5 students in office hours, so probably I'll stay masked in office hours. Mostly though, if just 1 student's there, we can take masks off. Or, but they said if you're in a crowded situation, then you should still mask. Seem reasonable? Also, if anybody prefers to be masked, just say it, and I'm happy to throw on a mask. I don't. It's certainly up to everyone's comfort. So I also posted. I thought you guys got email notifications when stuff was published to Gradescope, but apparently you don't. So I actually did Monday evening post the feedback for the test. I don't know if you saw that, but I posted the. Yeah, sorry, I probably should have emailed everyone. I just sort of assumed everyone got. Seems like people seem to know when stuff's posted pretty quickly, like when grades are published. But I guess I don't know. Or maybe you can set up Gradescope so it notifies you or something. I don't know. I don't know what it looks like from the student perspective very well. But anyways, so I did post feedback for the test there. Like I said, I will put. I need to make a Gradescope thing just set to upload the final write-up. But I'm also going to give the weekend grace period in case people want to take longer. So it's not, but there will be a problem set due next Tuesday. So, just keep all that in mind. Okay, sound good? But I'll definitely be in my office this afternoon. Well, after class today, this afternoon, and then Friday after class and Friday afternoon. So, any questions about anything related to that? Okay. I actually did find some better Mathematica code that I had about Lagrange multipliers. Why didn't that open? Open, please. No. Go find it. Okay, let me switch the share to this. Yeah, so because last time we started talking about these Lagrange multipliers, and well, this code's a little bit more elaborate than our usual Mathematica code, but we were looking at this example where we had the function x times y, the black lines, right, are the contour map of x times y. But you're supposed to be maximizing and finding the maximum values with respect to the constraint of being in or on this ellipse, right? So maybe I'll write it again on the board. Just the example that we had. So yeah, this is called constrained optimization, or Lagrange multipliers is this method. And we sort of talked about, so constrained optimization slash, it's called the method of Lagrange multipliers. Some of you may have seen this in econ. It's kind of a common thing in econ, although they don't explain to you at all why it works usually. And that's what we're going to do. So we're doing here. So the example that we had last time that I just kind of want to go through the details of was find the max and min values of the function xy with respect to the constraint that we're only going to care about the points that satisfy oh, was that louder all of a sudden? that satisfy. Now I said less than or equal to last time. So a lot of times we'll also just do equal to, just to sort of like say we're going to just restrict to that green curve, that green ellipse. But more generally, if you have an enclosed area or something, say something like that. And right, so we're looking at the maximum values of the function only within that region, because that green graph is the graph of x squared plus. No, what am I saying? I'm writing this incorrectly. I'm sorry. This equals this, which is less than or equal to 3. Sorry, that's what I meant to say. Right. The green ellipse in the picture is the x squared plus xy plus y squared equals 3, and less than or equal to 3 is the inside. Okay. So yeah, this region. Just draw it on the board. So it's this ellipse, kind of like that. This is the region satisfying that. This green ellipse is x squared plus xy plus y squared equals 3. And less than or equal to is inside there. Okay. Okay. And so what we said is we find the critical points. So the idea is to find the critical points within the region. And then 2 is going to be this sort of like Lagrange multipliers idea on the boundary. But let me recap what we. Maybe I should say not idea, but let's like identify the candidate points, right? The points that we have to plug in. Boundary. So we'd want to find critical points within the region, and we want to also do this Lagrange multipliers on the boundary. And then the idea here was, this was the thing that was that we just kind of got into at the end of class on Monday, which was, so the idea here was that the thing that we noticed, that you guys noticed, if you go back to the picture, is that just share this again. Was that you guys noticed that at the max and min points, this green curve was actually tangent to the contours of the function that we're trying to minimize. That at the non-maximum points, it's crossing contours, right? Because like, basically the value of x times y, like around this point, like it's equal to -1 at this point because it's the -1 contour. And it's going down if you go this way to -2, and it's going up to 0 if you go that way. So it can't be a max or min because it's going, somebody said it nicely last class, that it's going up in one direction and down in the other. Right? But at a point like this, it's sort of going down -2, down to -2, down to -2, just barely touches the -3 contour, and then turns back around and goes up to -2, -1, and so on, right? So that's where the minimum is happening, where the two curves are tangent, the contour and this are tangent. And then the thing that I was sort of saying last time, but I didn't have the visualization, is that you can actually do the gradient, because this is a function also, right? This x squared plus the constraint's a function itself. And so you can think of it as a level curve, and it has a gradient associated to it. So this is me trying to draw the gradient. It's a little bit hard to specify the gradient at a bunch of points, but like the gradient's perpendicular to the level curve here, right? I want to make this a little bit smaller so I can actually see this. Okay, so there's the gradient of sort of the g, the constraint function. And here's the gradient of the function x times y. right? So all of the, right, they're all pointing perpendicular. The gradient vectors are all perpendicular to level curves, and they're going in the direction of increase, right? And they're scaled so that they're longer if the vectors are bigger, if the gradient is bigger, you know, if it's steeper. So it's pretty shallow around the saddle point. And then if you overlay the two, oh, hello. This is where you can sort of see what's going on here. Like at all of these non-max min points, if you compare the blue arrows and the red arrows, they're pointing in different directions, right? But if you look around here, at this point, if you can see my mouse, then look, the red arrows and the blue arrows are pointing in the same direction. Or here, they're pointing in the opposite direction. Or here, they're pointing in the same direction. And down here, they're pointing in the opposite direction. So that's what I was saying. It's saying that the gradient, the idea is that the gradients are parallel. Because the contours are parallel, the gradients which are normal to contours are also parallel. So the idea here, if I go back to, I mean, it's a nice picture. Hopefully it's kind of evocative what's going on here. But let me go back to the, the blackboard. If the idea is that this is a level curve of G, right? We can think of this as a level curve of G. And so the constraint is parallel to contours of F. The constraint, I guess, is more like G equals constant. I'll write down the general form of Lagrange multipliers is parallel to contours of F at max min points, which implies their gradients because they're perpendicular to level curves are also parallel. And the way we write that down is that we say, you know, the gradient of F is lambda times the gradient of G for some lambda, for some scalar lambda at max min points. And so we want to find such points. But this gives us something to search for. Like this gives us equations to play with. Does that make sense? And so in our example, we said the gradient of F. Let's just see how this works, right? So the gradient of F is, I think it's yi plus xj. You do the partials of x times y, right? And the gradient of G is, I think we said it was 2x plus yi plus x plus 2y. J, just taking the partials of that x squared plus xy plus that y squared. And so if you set them parallel, so it's not setting them equal, it's setting them parallel. So, you know, so also, by the way, it doesn't, I guess I should say you could put the lambda on the other side if it's more natural, if it sort of looks easier. Doesn't really matter because it's parallel. You can move the scaling factor to the other side. And here it just looks nicer to me to say like, these are more complicated. So I want, you know, if I really want to write this all out, sort of formally, it's, but you guys can probably see what to jump to. lambda times yi plus xj. And so really that means 2x plus y equals lambda y, and x plus 2y equals lambda x, right? Just setting these component-wise equal to each other. Yeah, Sarah. It is, yeah. And in some ways, it's kind of a dummy variable because we don't necessarily really care what lambda is. We're just trying to find the x and y points. Yeah, although there are ways to interpret what it means in certain applications and stuff, but no, it's a good point. It's kind of, it's there as a, you know, an assisting variable or something. It's not really the main thing, but just because like in the picture, you know, these are parallel, but they're not the same length. The red and the blue vectors in the picture. At the max min points, they're parallel, but not the same length. So we're looking for such points. And then the other thing I said is we still have the constraint. Like this is 2 equations in 3 variables, which looks not good. 3 unknowns, 2 equations and 3 unknowns, x, y, and lambda. But we do have a third equation, which is the constraint equation. And so this is, I guess the point I was trying to make right in the class last time is that this is 3 equations in the 3 unknowns. And, you know, it can be a little bit of a bear to try to solve these, but usually there's some techniques or something, and certainly I will give you problems that are solvable, right? And solve. So if we solve, well, let's try this. Did people try it? I said you got a categorical imperative to try it between Monday and Wednesday class. I see one person nodding. The rest of you are staring at me like, we have lives, King. What do you think we're doing? All right, so one thing, there are different techniques, and there's actually a handout. We're gonna practice problems. I mean, basically, like at some point today's class and then all of Friday, we're just gonna be practicing, just trying to solve some of these in groups. But I guess I mentioned last time, at the very end last time, that one technique here would be to just solve those first 2 equations for lambda and then set them equal to each other so that you kind of get rid of lambda. And there's more or less slick ways to do that, but I will try to do it the sort of more straightforward way. But yeah, if there's any questions, please jump in. But okay, so here we could do, we could say 2x plus y over y is lambda, right? If I divide the first one by the y over, that's x plus 2y over x. So that's a way to sort of get rid of lambda if I want. You have to be careful though. Whenever I divide by x or y, what do I have to worry about? Yeah, if x or y is 0. So this is really only if x and y are not 0. So we have to spit off a separate case. Separate case is that if x is 0 or y equals 0. So we're going to have to come back to these. We're going to, come back to you have to come back and consider these cases, right? It's just sort of the logic of the algebra. But for now, if we have this, I guess we could sort of cross multiply, right? And we get 2x plus y times x is x plus 2y times y. And luckily, you can sort of see this leads somewhere nice. Because the x, y's cancel, and basically you get x squared is y squared, which means x is plus or minus, or y is plus or minus x. Now, that's exciting, because in the picture, if you look at where the max min points are, they do seem to satisfy x equals y or x equals minus y, right? They're all these 45-degree lines. So that already means, like, just compared to the picture, that we're on the right track. Yeah. Okay, so then we have two cases here. Y is x and y is minus x. So I guess the cases that we have to consider are y equals x, y equals minus x, x equals 0, and y equals 0. Right. And we can use the constraint equation is what I guess I'm saying. So we have the constraint equation. We haven't used the constraint x squared plus xy plus y squared equals 3. So use the constraint x squared plus xy plus y squared equals 3. So here, if we did that, we would just get x squared plus x squared plus x squared equals 3, right? X equals y. So that means 3x squared equals 3, implies x squared equals 1. So implies x equals plus or minus 1. And we get the points 1, 1, and -1, -1, right? Because y equals x. So that's case 1. Sorry, case 2. Well, okay, we do x squared plus x times -x plus -x squared equals 3. And so we get x squared minus x squared plus x squared. So that means x squared equals 3, which means x is plus or minus the square root of 3. Again, you should be comparing to the picture. It's kind of nice. Like 1, 1 looks like the right place on the picture. -1, -1 looks like the right place. And now over here, because y is -x, we actually get like √3, -√3, and -√3, √3. So now we found these. We basically found the 4 points. But I do need to deal with these other cases that we had to worry about. You can actually, let's see. So, I mean, you could just have more points to check. Like these would create other points you could check, and then you want to plug them all into the function. Remember, we're trying to maximize and minimize some function. So once you have a list of points, you can just plug them all in and see which gives you the max value, which gives you the min value. So if we do case 3, x equals 0 would imply, plug in x equals 0 there would imply y squared equals 3. So y is plus or minus the square root of 3. And so we get 2 more points, I guess we could check, which are 0, √3, and 0, -√3. Or sometimes you can actually go back to the, so this satisfies the constraint, but it may not satisfy the other, like, I guess there's 2 things, there's 2 ways you can go here. You can either find too many points and just check them all, or you can actually rule out these points in a different way, which is that I think that these don't actually satisfy probably the second equation, the second Lagrange equation. Right, if you look at x plus 2y equals lambda x and plug in x equals 0, I think you get 2y equals 0, which this doesn't satisfy. So I'm saying there's two ways to go about it. You can either try to rule the points out, or you can just check extra points. It's not that big a deal to plug extra points into a function and see what, like this won't be the max or min value because it's not actually. Yeah, like I'm saying, like these got spun, right? It's because of the algebra that we did, we do have to consider these kind of points, or we have to consider the case when x is 0. But I could either say this, or I could say, I guess I could say from here also that, you know, x plus 2y equals lambda x would imply that if you plug in x equals 0, you get 2y equals 0, which implies y equals 0, which means these aren't actually points that satisfy these points don't actually satisfy all three equations. So we don't actually have to check them. I kind of like this better just because it's like, we should really only check points that satisfy all three equations. And sometimes you do find extra points you have to check, but in this case, you don't really have to check these points. They really got spun out of this algebra that like, it could have been the case that there could have been important points. And I have examples where there actually are points that are important where you're like, if you try to divide by 0, you actually miss an important point. In this case, you don't really miss an important point when you do that. Because this would imply x equals 0 in this equation implies y equals plus minus root 3. X equals 0 in this equation implies y equals 0. So those are contradictory. You can't have y both be 0 and root 3 at the same time. So the point is like these points don't satisfy all three equations. So the x equals 0 case doesn't really lead anywhere, I guess is my point. Sorry, I mean, maybe I should have just like let us check extra points and just not worry about it. But because once you have a finite list of points to plug into the function, you can just plug them all in and see what gives you the maximum values. So, okay. Let me just finish this off. I think y equals 0 is very similar. There's sort of really a symmetry between x and y in these, right? Because here you would get x squared equals 3. And you would get, I erased the second equation, but I think the second equation was y plus 2x equals lambda y. Plugging in y equals 0 would imply that x equals 0. And so you can't have x squared equals 3 and x equals 0 simultaneously. I guess that's what I was trying. That's kind of why I crossed those out. That's kind of the logic. Simultaneously. So no more point, no extra points to check. So we really just have those 4 points on the boundary, right? So, but inside the region, zero is a critical point is the only critical point of the function x times y, which remember is the function that we're trying to maximize and minimize here. And so really we end up with a total of 5 points to check. We know the maximum values have to occur at either at any of these points, right? Right, these are the 5 points that we've identified. I guess I should put like that. Right, those are the 5 points we've identified. And if we just plug them all into f, right? F of 0, 0 is 0 times 0, which is 0. F of 1, 1 is 1 times 1, which is 1. F of negative 1 is negative 1 times negative 1, which is 1. F of root 3, negative root 3 is the product of those, which is negative 3. And f of negative root 3 comma root 3 is also negative 3, the product of those. And actually, if you go back to the picture, you really can see it, right? Like the maximum value is 1 at these 2 points, and it's negative 3. The minimum value is negative 3 at those 2 points. So there is a critical point inside, but it's neither a max or a min because it was a saddle. Sort of makes sense that it's neither a max or a min. But basically, this is our max value, and this is our min value. That's what the question's asking, is like, what's the maximum minimum possible values? Okay. Questions about that? Yeah. Leah. We have multiple points where the maximum is achieved and where the minimum is achieved, right? But the maximum value, if I ask, think about the way the question's often be worded is like, what's the maximum value of this function with respect to this constraint. And in this case, the maximum value is 1. But yeah, it can be achieved at multiple points. Okay. Other questions? Let me just say in general, I may as well just write the general like Lagrange multiplier thing. I mean, we kind of did write it down already, but and I'll even write down, we can even do it for functions of 3 variables or more, functions of 7 variables if you wanted to. So in general, if we want to find the max min values, maybe I'll write it as the general like 3 variables like of f of x comma y comma z with respect to the constraint g of x comma y comma z equals c. Then the Lagrange multiplier says basically set the partials parallel or set the partials like as a scalar multiple of each other and use the constraint. So yeah, Lagrange multipliers. You basically say f sub x is lambda times g sub x, f sub y is lambda times g sub y, f sub z is lambda times g sub z, and g equals c. And this is 4 equations and 4 unknowns, x, y, z, and lambda. Okay, that's kind of like the most general form of this. So let's look at this handout I have. Yeah, so I put this handout on the handouts page also. So this kind of says the same thing that we just said, right? We're like, you're trying to maximize or minimize a function with respect to a constraint. We discovered that the gradients must be parallel to the max min point. This plus the constraint gives us equations to solve. And like I said, one of them is like, if you want to take different approaches, like I just gave a couple of things that show up in the algebra a lot of times. So the first one is like what we did in the example, which was we just got rid of lambda, right? But there are other times where sometimes you can solve for x, y, and z in terms of lambda, plug back in and give you lambda, and then that'll tell you x, y, and z. I mean, you have to see it, but so really then I just have problems. Let's do problems. You guys want to do some problems? Probably we'll start this today and then we'll probably just continue on Friday, because all you can really do with these is practice. So let's break into groups, shall we? How should we break into groups today? Any ideas? What did we do? What did we do before? What did we do by? Didn't we line up at some point? Oh no, we never did that. Maybe it was in my other class. I guess we could do that. Do you guys want to figure that out yourselves, or you want me to? Okay. So grab some of the people around you and go to one of the boards. You can go, there's 9 boards around here. Just get to groups of like 3 or 4 and go to a board, grab some people. I can push you into groups if you want. Let you guys figure it out. Yeah, remember, take turns who's writing so other people can write on the, You can pull the handout up on your iPad or whatever. Introduce yourselves if you don't know each other. Be nice and helpful, try to help each other. All that stuff. So you guys are a group, you guys are a group, you guys are a group. These people over here are a group. Someone can join them if they want. Or you guys can start to form groups. Sorry, I don't know, maybe I should have done this more. How do we want to make groups here? Hi, Gary. Wait, you guys are a group right here. You can join whichever one you want to join. You guys are a group. I guess I'll stop recording. So the rest of class group work, stop recording.